Hi, we are the members of Team 4. This presentation is in fulfillment for the requirements for the assignment CZ4046 Intelligent Agent. The scope of today's presentation are as follows. Firstly, we will explain the architectures that we have designed, namely hybrid and BDI. Then the features of each architecture such as world exploration, target selection, path planning, refueling strategies, and decay time consideration. The team synergy section will describe how the two agents coordinate their movement. Finally, we'll discuss our result and analysis.
The first architecture which we used is a hybrid architecture. Using this architecture, the agent's controls are separated into different layers, with the higher levels having lower precedence. In this case, we separated the controls into 4 layers. After the agent has sensed its surroundings and updated its working memory, it will decide its next action by going up the layers. Using the hybrid architecture, we have came up with 2 versions of agents. As you can see in this table, the algorithms used for refueling, selecting targets, and planning paths are the same. The only difference is in how each version explores the world. For refueling strategy, both versions of the agent are using the refueling threshold to determine when to refuel. For target selection, the agent will always choose the nearest target. For path planning, the A-star algorithm is used. For the exploration algorithm, the first version of the agent moves around the world in the spiral direction, while the second version moves around the world diagonally. As I've explained in the earlier slide, in the first layer, the agent will ensure its survivability by making sure it has sufficient fuel. It does this by checking these 3 factors. Now, let me explain how to calculate the threshold value. First, we calculate the distance between the agent and the refueling station. Then we measure the ratio of this distance to the area of the tile world. Next, we calculate the value of the fuel buffer by adding the length and width of the tile world and dividing the total by 8. After some experimenting, we found that 8 is the best value to use here. Finally, the threshold value is calculated by summing up the distance and the multiplication of ratio, log square of time steps, and the fuel buffer. The purpose of the multiplication is to provide the agent additional buffer by estimating the probability of running into obstacles on the way back. By having this additional buffer, the agent will have enough fuel to bypass any obstacles on the return trip to the refuel station. To calculate the number of steps remaining, simply minus the current time steps value from 5000. After calculating those values, the agent can now decide if it should refuel. It will proceed to refuel only if these 2 conditions are met. The first condition is when the agent's current fuel level is equal or lower than the threshold value. This ensures that the agent will have enough fuel for the return trip to the refuel station. The second condition is when the number of steps remaining is greater than the threshold value. If the agent has enough fuel to last until the end of the run, then it should not waste time to refuel. After the agent has decided that it does not need to refuel, the next step is choosing a target. To do this, the agent will always check the following factors: number of tiles it is carrying, whether a hole or tile has been detected or both, and how far away they are from the agent. A tile or hole is considered detected if it resides in the agent's memory. This picture represents the agent's memory, and in this case, 4 holes and 1 tile were detected. The distance is calculated by measuring the number of steps required by the agent to reach the object, and in this case, the distance which is represented by the yellow line to the tile is shorter. Based on those factors, the agent can now select the target based on the following conditions. In the first scenario, the agent is carrying 1 or 2 tiles, and if a hole or a tile has been detected by the agent, It will do a distance comparison and proceed to the closest object. In this case, the agent will go to the tile as it is closer. Otherwise, if either only tiles or only holes have been detected, the agent will proceed to the respective object that was detected. In the second scenario, the agent is carrying exactly 3 tiles, and if a hole has been detected, the agent will proceed to it. And in the third scenario, the agent is not carrying any tile, and if a tile has been detected, the agent will proceed to it. Finally, if the agent does not need to refuel and no target is found, we will proceed to explore the tile world using one of the 2 exploration algorithms. For the spiral movement, the agent will move along the spiral path as shown. The advantage of the spiral movement is that the agent will be able to explore the entire tile world without overlapping any explored region. However, it has one big disadvantage. As you can see, as the agent is moving along the spiral path, if a tile spawns at the place where the agent has just explored, it will take the agent a long time before it will revisit that spot again. So by the time the agent comes back, the tile will have disappeared. And for the crisscross movement, the agent will move along the diagonal path as shown. The advantage of this movement is that the agent will be able to traverse across tile world quickly. However, it also has one big disadvantage. As you can see, as the agent is moving along the path, if a tile spawns just outside the sensor's range, it will not be able to detect it, even though it is only a few steps away.
Now I'll talk about the BDI architecture. First, it runs the belief revision function and revises the beliefs by sensing the world. Next, the delivered part will generate an intent, and according to the intent, it will generate a one-step plan. Next, it will execute the one-step plan. The implementation of the BDI agent is split into 3 main parts. First, it sends the world and updates its belief. Next, the think portion where the deliberation and planning takes place. The deliberation outputs an intent and the planning outputs a TW thought according to the intent. The TW thought contains an action and direction. Lastly, the act function performs the action and direction accordingly. For the belief, you run the belief revision function and sense the environment to update its beliefs. For the intentions, you have 4 types of initial intentions: the refill, go whole, go tile, and explore intentions. Under the deliberation, there will be the options function where new desires will be generated. However, our implementation is such that there are no desires generated. For the filter, you output an intention according to the updated beliefs, the desires, and list of intentions. And in this case, there will be no desires, and the intention will be fixed intentions. And how does the filter work is that you will first check if the agent does not have enough fuel to reach the fuel station, and hence it needs to refuel. Or next, it is near a fuel station and do not have enough for a round trip, and hence it needs to refuel too. Thirdly, you'll check if there's a hole and there's a tile nearby, and the agent also has a tile, and hence you'll go to the nearest object. Next, if there's a tile nearby, you'll simply go to a tile, and if there's a hole and the agent has a tile, you'll go to that hole. Otherwise, you explore the map. For the first case where it needs to refuel, it will check if it is already at the fuel station and refuel. Also, it resets its next checkpoint to the one nearest to the fuel station. Otherwise, if the station is blocked, it goes to a location nearest to it instead. The second case where it prefers a hole, it drops the tile into the hole if it's under the agent, or moves towards the hole. The third case where it prefers a tile, it picks the tile if it is under it, otherwise it moves to the tile. Finally, if there are no tiles or holes, it will decide to explore in the direction of the next checkpoint instead. The act function will perform the plan according to the TW thought. For the pickup tile and put tile in hole, you will have to remove it from the agent memory and memory grid too. Some important considerations were to minimize distance to refill and also to maximize places explored. Minimizing the overlap and other agent and routes will allow the agent to maximize exploration. The agent will minimize distance traveled to refuel by refueling early when it is near the fuel station. Next, we have checkpoints for exploration. There are 4 checkpoints, and the agent moves in the direction of the arrows. Next, we change the checkpoints further from the edges to maximize exploration. Next, we minimize the overlap with the other agent by changing the checkpoint such that there's an allowance away from the other agent. And we minimize routes that will be traveled twice by checking if it has exceeded the checkpoint and it simply skips to the next checkpoint instead. And we have 2 versions of BDI agent, version 1 and version 2. And the difference is for the target selection, the version 1 will simply go to the nearest object, such as the tile or the hole. However, for version 2, it will favor a hole if the agent has already more than 3 tiles.
The diagram shows the effects the decay time have on the agent's behavior. By having a higher decay time, the agent retains more information about the environment. However, there are risks of storing outdated information. On the other hand, having a shorter delay time, agent retains less information on the environment, but there are no risks of storing outdated information. If the environment is very dynamic, having a shorter decay time might be better as agent tends to forget outdated information quickly. However, if the environment is static, having a higher decay is more beneficial as the information the agent retains is more valid. We have decided to select the 50 decay time because it's more beneficial for the agent to have more information of the environment. 50 is long enough to retain useful information but also short enough where the memory will not be cluttered with outdated information. In this section, we will talk about the movement coordination that we have implemented. We've decided to utilize the divide and conquer approach for how the agent should carry out exploration. The first step of the divide and conquer approach, we split the environment into 2 equal regions. Each agent is then assigned to explore one of the 2 regions. The first advantage of using this strategy is its simplicity. Agents are not required to communicate with each other as the search area do not intersect. Secondly, by doing so, we have reduced the search space of each agent. Because Tower has a dynamic environment, by reducing the search space, the time it takes for the agent to revisit explored location is shorter, thus allowing the agent to see more. This means that the probability of agent encountering tiles and holes before they disappear is higher. The diagram shows the 2 methods of splitting that we have used. The first method is dividing the environment into half using the midpoint of the x-axis. The second method is dividing the environment into half using a line drawn from one corner of the map to the opposite corner. The advantage of the first method is that since the environment is rectangular in nature, the codes for the movement algorithm implemented for the original tower can be used for this without much modification. This is because the original tower is also rectangular in nature. The disadvantage is the agent on the right half of the area is further away from the refueling point. The advantage of the second method is that the refueling station is equally placed between the two regions. The disadvantage is that the movement algorithm needs to be modified as the regions are now in a rectangular shape. We have decided to use the second method as it allows both agents to be able to refuel when they are near the refueling station, instead of relying on the refueling threshold. As you can see from the table, for parameter 1, BDI2 agent achieved the highest mean score of 74.07 with a standard deviation of 6.79. For parameter 2, BDI1 agent achieved the highest mean score of 722.08 with a standard deviation of 16.47. For parameter 3, BDI2 agent achieved the highest mean score of 218.66 with a standard deviation of 14.29. These results show that agents using BDI architecture has a better performance compared to agents using the hybrid architecture. Even though BDI1 scored higher for parameter 2 compared to BDI2, the standard deviation of BDI2 agent for all the parameter is lower. This means that BDI2 agent has a higher stability compared to BDI1 agent. Thus, we have decided to use BDI2 agent for the competition. We have now come to the end of our presentation, and thank you for watching the video.